Okay, good morning, everybody. Thank you for joining us for the next webinar in our series here at Analytics. Today's presentation is going to be given by my colleague Alex Watson, and it's going to be focusing on our solutions for cleavage and deprotection resulting from the oligonucleotide production. Just a couple of housekeeping points here to consider. So, like I said, the session will be recorded. The recording will be available if you wanted to watch it offline or to share with any colleagues. So just pop a note in the chat box. I will stick our sales inbox address on there for anybody that wants it, and we can send it out after. Any questions that you've got throughout or at the end, again, pop in the Q&A or the chat box and we'll try and get to those once Alex has finished the presentation. It should last around 30-35 minutes today, and then we'll keep some time at the end for some questions. So without further ado, I will pass you over to my colleague Alex, who will dig into his presentation. Thank you very much.
Thank you very much, Duncan. Okay, let's get going. So today, as Duncan mentioned, we're going to be looking at the oligonucleotide synthesis workflow. So we're going to be focusing on the cleavage and deprotection step, which traditionally it's the bottleneck for oligosynthesis. With all of these webinars, there's going to be a strong focus on the application side of things. So I'll be spending quite a lot of time talking about oligosynthesis, the traditional bottlenecks, and also presenting wave prep as a solution for this bottleneck. So just to start off with a little bit of background, I'm sure a lot of our listeners already know what an oligo or an oligonucleotide means, but for those who don't, oligonucleotides are short sequences of nucleotides, typically 20 or fewer. Nucleotides are the building blocks for RNA and DNA. So there are 5 different types of nucleotides. For DNA, we have thymine, cytosine, adenine, and guanine. And for RNA, we have thymine replaced with uracil. So it's the specific sequence of these nucleotides that denotes a genetic function or gene. So these nucleic acids do occur naturally, but it's now also possible to produce them in the lab using an automatic synthesizer. So there's a growing trend of these labs bringing synthesis in-house rather than using large external suppliers. And the reason for this is that the technology is just getting more accessible, and it's easier to do it on a lab scale in your own lab. So what are oligos used for? The importance of oligos has dramatically increased in the last decade, particularly in the last sort of 2 to 3 years. There's a long list of potential applications, but here are a couple of big examples. So first, it's the use in research and diagnostic applications. So be it ordering custom oligos for research purposes or ordering custom PCR primers for PCR amplification of specific nucleic acids, or you could be doing quantitative PCR for diagnostic purposes. Therapeutic applications are also a big one, and particularly so in the pharmaceutical industry. Be it gene therapy, where encoding and delivering a functional gene to a patient, or it could be the use of oligos to modulate gene expression in a patient. And this could be used to help off viral infections, treat cancer, and prevent tumor progression, as well as treating respiratory diseases or specific genetic disorders. So for example, cystic fibrosis or DMD. So yeah, a really huge range of applications from research to pharmaceutical, and we're seeing a really growing trend in this. And we envision that in the next 5-10 years, a lot of particularly therapeutic approaches are going to be based around oligos. How do we produce oligonucleotides? So how are we doing this synthesis? There are a few different techniques, but by far the most established and widely used is solid phase synthesis via the phosphoramidite method. So here we're using a solid support and attaching our first nucleotide via a linker. We then, for every cycle of this process, we're adding a single specific nucleotide in a growing chain in the 3 to 5' end direction. And we're doing this on an automatic oligonucleotide synthesizer, which may look something like this. It's just adding a single nucleotide at a time with a few wash steps. Obviously, that is a simplification, but yes. Here's an illustration of that phosphoramidite cycle. As you can see, if I get my laser pointer here, there are 4 stages: detrylation, coupling, oxidation, and capping for every nucleotide addition. So for every nucleotide that we add on to this chain, we do this 4-step cycle. This is specific for DNA synthesis, but the process is pretty similar for RNA. So let's look at each of these stages in a little bit more detail. Just note this is going to be a bit of a simplification just for the purposes here, give us a nice idea. So firstly, we've got our solid support, and this is what's actually holding our oligo. So we're using a linker to connect our solid support to our first nucleotide in the nucleotide chain. We've got our protective group. This sits on our nucleotide and it prevents any unwanted side chain reactions. First stage being detrylation, we have to remove what's called the 5' DMT protecting group. So this protecting group prevents an nucleotide coming and binding on when it's not ready to do so. So in this process, we remove that protective group. We're now ready for coupling, in which the next nucleotide in our specific sequence is presented to our oligo for binding. As it sounds, it then couples, and we then perform an oxidation reaction, which forms that stable phosphate triester backbone between our oligos. We now have to perform capping. So because 100% coupling is impossible, we're always going to be left with some unbound 5' ends. So in an oligo in which the next nucleotide wasn't presented to it and it didn't bind. And we term these things shortamers. It's really important to get rid of these shortamers or terminate them, because if not, we're going to have a mix of different nucleotide lengths, and we're also going to have mutations in our oligonucleotide sequence. So by capping them, we prevent their involvement in subsequent monomer additions. So they are now removed from this cycle for the next nucleotide addition. Now that we've performed all of that and we've capped off the shortamers, we're now ready for the next detrylation cycle, in which we'll remove our DMT group and the next oligo. So on until we've built our perhaps 20 nucleotide oligo. So after synthesis, this is what we're left with. So we're left with our specific oligo sequence. Our protective groups so far have prevented any unwanted side chain reactions, and we're also bound to our solid support via our linker. Firstly, we perform cleavage. As it sounds, we're just cleaving the linker group. So we're removing our oligos from our solid support. We'll then perform deprotection, and just a chemical process in which we remove those protective groups, and we're left with our final product. At this stage, the oligo will still be interacting with the solid support. It's not physically bound, but it has an interaction, so it stays connected to our solid support. By adding water or any aqueous solution, we elute the oligo away from the solid support, collecting the oligo. So that's sort of the synthesis and C&D process illustrated. And that would be our final product, in which we do downstream purification steps, QC and analysis, before storing the final product, typically via freeze drying. Here we can see what that illustration equates to in an actual lab in a physical laboratory environment. So here's the oligonucleotide workflow. We can see, starting at the solid phase synthesis, we've got our large-scale automatic synthesizers. We'll then perform cleavage and deprotection manually. We'll elute oligos, cleaved oligos from the solid support, perform purification, and then do analysis before storage. And a really important thing to notice here is that you'll see the synthesis step and all of the quality control steps involve modernized automated technology. Cleavage and deprotection, as well as elution, remains the bottleneck in this process. It involves multiple labor-intensive time-consuming steps where we can very easily introduce error to this workflow. So let's have a quick look at conventional cleavage and deprotection. How are we doing this in the lab? So here we're physically soaking our solid support bound oligos in cleavage and deprotection reagents. So typically, your C&D reagents, they're fairly nasty chemicals. So it could be ammonium hydroxide, it could be methylamine or AMA, or a combination of the three. And these are both corrosive and flammable. So it's a pretty bad mix. We have to take really serious care with the handling and the storage of these chemicals. We're soaking our oligos via manual pipetting. So it normally involves a lab user manual pipetting these reagents into a deep well plate, or it could be a large column or medium column containing our solid bound support oligos. Then, depending on the oligo type, we use a few different heating methods. So typically, C&D is performed via conventional heating somewhere between 40 and 80 degrees Celsius. For thermoliable oligos, so oligos that might degrade at elevated temperatures, we have to perform ultra-mild C&D. And this is particularly tricky. Normally, we have to carry out cleavage and deprotection at room temperature for extended periods of time, sometimes 24, 27 hours. Finally, just to remove that excess C&D reagent, we have to perform an evaporation step. So this is done after C&D is performed, before we can elute our oligos from the solid supports. So what are the limitations of this conventional approach? I've sort of touched on some of them as we went, but just to recap, firstly, it's the long reaction time. So 4.5 hours, even up to 27 hours for those ultra mild C&D conditions. Again, evaporation is required after C&D. It takes a lot of time, and it's also an opportunity in which you might degrade your oligos or introduce some sort of contamination. At room temperature, the reaction takes place for a long time, and also takes place with low yield. So by heating to 40 or 80 degrees, we can speed up the process, but there's always the risk of degrading our oligo. We're typically doing this in a heating bath or a conventional heating system as a hot plate, and these have really poor temperature control. And that can cause a couple of things. If the temperature is too hot, we're going to cause degradation, or if it's too low, we're going to have really poor yields. We might not get complete C&D. This also opens the doors for a lot of possible errors. One of the big ones is there's multiple C&D methods, be it the reagent use, the temperature that you're heating to, and the amount of reagent to use. And you need to pick the particular C&D strategy based on the oligo you've got. And that takes up a lot of thought. If you pick the wrong one, you might cause degradation, or you might have poor yields. Again, it's a manual step. So we're introducing the chance of human error, be it not dosing your C&D reagent, or introducing contamination between your oligos. It's labor intensive. It takes a user a lot of time to do all of these pipetting and drying steps. And that means that it's really difficult to scale up. It's hard to bring that from lab scale to large scale production of oligos. It takes up a lot of C&D reagent. We're having to physically soak the oligos in reagent. So it uses a lot of that, which is not a cheap approach. There's also a lot of safety limitations. If you imagine we have these particularly nasty chemicals, ammonium hydroxide, for example, on in a conventional heating bath at say 70 degrees overnight, your user's continuously exposed to ammonia vapors, and it can be really dangerous. Now that we've covered the background, we've discussed the limitations of traditional C&D, let's have a look at a solution. So here is Milestone's wave prep system in the background there. So this is designed for automated gas phase cleavage and deprotection. So let's have another look at that workflow. So here you can see that we've replaced that manual step with wave prep, and that's covering the entire cleavage, deprotection, and elution step. So to streamline that entire process, we now have an automated techniques from the start of synthesis all the way to quality control. I've now just got a couple of the aims for the system. So when Milestone were looking to design this, they spotted this gap in the workflow, and they came up with a few aims for what they want wave prep to be able to deliver to the lab. So they want it to be fast and automated cleavage and deprotection. They want it to have really high productivity with superior product yield and quality. They want to revolutionize the safety aspect of it, move away from exposure of ammonia vapors. And they also want to make it really easy to implement. I've now just got a quick video before we look more into wave prep. I think it's a nice way of just visualizing the system more so that when I talk about it, it makes a little bit more sense. So here you can see the oligos that automatically brought into our cleavage and deprotection reactor. So the user simply places in the uncleaved and deprotected oligos. It could be columns or deep well plates. The system then automatically shuts, bringing those oligos down into our 10-liter reactor. Automatically seals. As it's a pressurized unit, we just need to close the clamps. Just a hand tightening procedure. We then have a safety lock that comes in and stops you from opening it whenever it's pressurized. The system automatically loads our C&D reagents, so there's no handling of C&D reagents at any point. It'll fill up to 400 ml. The microwave system will then start delivering microwaves, and will heat up that liquid C&D reagent, vaporizing it, and creating that reactive gas phase, which actually carries out the C&D. So you can see we get to temperature really quick. We have a number of sensors that control and make sure that we have a really stable temperature and really sensitive temperature control. After the run, we've got really rapid cooling. We'll depressurize. We'll also perform purging runs to get rid of any of the C&D reagents, and we'll pump the C&D liquid reagent out of the reactor. After we've opened the clamps, then the system's ready to open. You'll notice we have these very powerful exhausts here. If there's any residual vapors, even after purging, they'll then be brought away from the user. Once your plates and columns of deprotected and cleaved oligos are out the system, you can then take them on and they're ready for elution. So really easy and sleek solution. So let's dig a little bit deeper into sort of the individual concepts of the system, and there's two main ones. So firstly, as the market leaders in microwave technology, wave prep harnesses microwave power to really efficiently and precisely control temperature, and that's really critical for dealing with oligos. We're then using microwave power to perform gas phase cleavage and deprotection, rather than physically immersing our oligos in reagents. For the microwave reactor, we're using what's called single reaction chamber technology. So here we have our magnetron, and that's delivering 1,500 watt of high density microwave power. Those microwaves will be guided via our waveguide into our 10-liter reactor. And this is where the oligos are lowered and sit into. These microwaves interact with our liquid phase C&D and generate that gas phase that does the cleavage and deprotection. Quite a unique feature is a cooling jacket that surrounds this reactor chamber. So we use a circulating chiller, which comes with the system. And this chilled jacket has a number of benefits. So firstly, if we're operating at a high temperature for a very long time, this cool jacket will kick in and it will drop the temperature, prevent any overheating internally of the system. Secondly, we can use it to cool down really quickly. So it's a really efficient way of bringing that reactor down to save temperatures in which we can open it. so it cuts down our run and cooling time. And then another sort of benefit that we're sort of seeing now is the impurity levels. So one of the important things with cleavage and deprotection is to reduce the impurities. We want to hold our oligos at the set temperature for the shortest amount of time possible. So firstly, we're using microwaves really efficiently, hitting our target temperature in a matter of minutes. We're then really stably holding that target temperature until the run's done, the minimum amount of time as possible. We're then rapidly dropping the temperature using our cooling jacket, bringing it back down to room temperature. And that helps to reduce the levels of impurities. And it's one of the reasons why we're getting lower impurity levels using this technique. So this is a view for inside of our reaction chamber. As you can see, we have rods that attach to our top plate, and these are what hold on either our deep well plates or large columns that hold our resin. The C&D reagents sit at the bottom of this reactor, as I mentioned. They're coupling with the microwave energy that's coming in from the bottom here, rapidly raising the temperature and vaporizing to generate the reactive gas phase. And that gas phase, it permeates either our columns or our deep well plates, interacting with the oligos and performing cleavage and deprotection. So we're not soaking our oligos in liquid phase, we're just doing it all in gas phase. Given the sensitivity of oligos, it's really important that we have fine temperature control over this gas phase. We've got multiple sensors in this reactor. Firstly, we have a pressure sensor. It's used to prevent any overpressurization. We have a liquid phase detector, which sits down here on one of these rods. That's measuring the temperature of our liquid phase. And most importantly, we have our gas phase temperature sensor. And this is really important because it's measuring the gas phase, and this gas phase is actually what's interacting with our oligos. So really, this is the temperature of our oligos. And for that reason, that's what we control this entire process of the temperature of our gas phase. So the system uses a PID algorithm to modulate microwave power constantly through the run to make sure that the oligos are experiencing a very specific temperature that we've set. So there's multiple different sample holding options with wave prep. It's really flexible in that way, and that means that we're able to work to a really wide range of production scales. So firstly, we've got the room for space for 6 96 position deep well plates. That's really popular for synthesis of small batches of custom oligos. It's what a lot of our customers use wave prep for. We then have our small to medium sized columns here. So this is a PTFE insert plate with 70 positions, and you would insert the small to medium columns in these positions. And that's perfect for sort of the nanomole to micromole scale. We can then move to our larger solutions. So on the left here, we have our 55 mil position columns. And on the right, we have our largest 750 mil columns. So here you'd be inserting manually the resin into these large columns. And these large solutions, they allow us to work up to the millimole production scale. So we're working in the entire production scale. Another nice feature is that these columns and support plates are all interchangeable. The user can do this himself in a matter of minutes. You simply take one out and put the next one in. You can also run with mixed setups. So for example, you could have one plate of your 55 mil, 355 mil columns. You could have your small and medium plate in the middle, and then at the top you could have maybe 2 96 deep well plates all in the same run. So it's really flexible in that way. As long as we're immersing our oligos in that gas phase, it doesn't really matter. For our deep well plates, we've got the option of using a hydrophobic porous filter. This allows ammonia gas permeation to carry out C&D, but it prevents water droplets from entering. These water droplets could cause elution. So yeah, it's a really handy option for the deep well plates. And you'll also notice on our columns, when we're using the exact same material. Again, it's doing the exact same thing. It's letting the ammonia gas permeate into our columns. It's preventing water droplets from entering. And as I touched on briefly, so the joys of using gas phase is that sample holding is really flexible. As long as gas is entering those columns, it doesn't really matter how they are in there. So we're more than happy to help with custom solutions if there's a specific column type that you want to use, a specific resin volume that you're working towards. We're happy to help you create a custom solution within WavePrep. So what are the advantages of performing cleavage and deprotection in the gas phase with Milestone's WavePrep? The big advantage is time. So if we look on the right here, we're looking or comparing the standard synthesis process, the top here, with the synthesis process using WavePrep. So the immediate difference that you'll spot there is that we're bringing the cleavage, deprotection, and evaporation step into one single step. We're also reducing the time that takes. So for most oligos, we're getting cleavage, deprotection, and evaporation. Obviously, there's no evaporation, down to about an hour. Other advantages include the fact that we're not soaking our oligos in liquid reagent. It means that evaporation is not needed. It also means that we're massively saving on reagent use. There's no risk of cross-contamination. We're performing cleavage and deprotection simultaneously. There's a lot fewer methods for different oligotypes. That's really handy in terms of time spent picking the right method for an oligo, and also the time that we're spending designing these methods, as well as just preventing any issues or mistakes, applying the wrong method to an incorrect oligo. We're also getting high cleavage and deprotection yields, particularly so for complex oligos, the thermoliable ones, and also the ones with quenches or dyes to them. So functioning and control of WavePrep. Let's have a look at the operation sequence. So firstly, as we saw in the video, the system automatically lowers our oligos down into the reaction chamber. We'll then seal the pressure clamps. The safety interlock will then lock this in place so that during operation there's no risk of a user being able to open the clamps. The reagents are then very carefully pumped down one of our rods. This means that there's no splashing, there's no risk of the liquid contacting the oligos. We'll then begin the microwave heating. We'll vaporize our liquid phase, generating that reactive gas that performs C&D. After the run's done, we'll then do our rapid cooling of the reactor. The liquid C&D is pumped out. We'll then perform purging to remove any residual C&D vapor phase that's left. We'll then open the clamps and the system will automatically rise and bringing out our cleaved oligos ready for elution and downstream processing. So the entire handling of all the reagents and gases at the end of the run is handled by WavePrep. So we have what we call the pump station attached to, it's a separate unit that sits alongside WavePrep that handles all of the reagent dosing. So we'll have a supply bottle here, and we'll also have a waste bottle. At the start of the run, the system will automatically load from the supply bottle into the reactor. At the end of the run, it draws this out into the waste bottle. We have standard lids on these, so I believe it's GL25, which means that rather than having to decant from, say you buy your reagent straight from a provider, rather than having to decant it into a specific pump station bottle, you just screw on the pump station lid, completely removes any handling of the reagents. On the top here, we have an exhaust line for each bottle, and we also have quick fit fittings so that you can quickly attach these, and means you can move around the lab still with the lid on rather than having an open bottle. The system has detectors in each of these bottles, so you'll be able to monitor the amount that you have in each of these bottles from the software. And the software actually won't let you start a run unless there's enough in the supply bottle to commence, or if your waste bottle is quite full and at the end of the run there's going to be an issue with overfilling. So it physically won't make you make a mistake there. An interesting point is the option to reuse reagent. We've seen that actually the concentration of the ammonium hydroxide isn't dropping considerably during a run. So if you're really pressed to reuse your C&D reagents, there's also the option of potentially reusing it. So with all those temperature sensors and pressure sensors, we need a good way of visualizing this. So mid-run, we'll always be able to see this temperature profile. We also have quick view options where you just see one temperature if you're glancing across the lab. But for this full trace, this is what's exportable and visible during the run. We have a number of different sensors that we're looking at. So firstly, T1, so that's the gas phase, and that's the important one. That's what the system is controlling and then monitoring. So as you can see, we're bringing up from room temperature to our target temperature, which in this case is about 55 degrees. We're doing that in about 10 minutes. We're then really stably holding at our set temperature till the end of the run, and then we rapidly cool. You can see in T2, so this orange line here, this is the temperature of our jacket. In this run, as we're working quite a low temperature, we never actually hit the temperature in which the chilling jacket would kick in and cool this down. So it just continuously rises throughout the run. If it did go any higher, the cooling jacket would kick in and it would bring it down to room temperature. We then have T3, which is the temperature of our base load. That's that sensor that was sitting in the liquid phase. As you can see, we're rapidly bringing that up. So it's one of the benefits of microwave power. We're really able to keep things up very fast. We're bringing that to the vaporization point where it vaporizes and it sort of plateaus as we've got a constant cycle of vaporized C&D reagent. You'll see that we have a pressure safety limit. So in this case, it's about 17 bar. We put this in, it's just a safety backup. We should never ever hit that high, but if it does get to 17 bar, although this isn't the maximum capacity of the system, it'll stop the run, so it'll abort the run, and you can bring that to any pressure that you'd like. Finally, a quite nice thing to see is the microwave power. You can see it's this black line here, so at the start of the run, we're using a lot of power to rapidly vaporize our C&D reagents. Once we hit target temperature, it drops down, and we're just modulating it, using it just when we need it to maintain that really stable T1 temperature. And these are fully exportable. You can export as a sort of PDF of this graph, or you can export in an Excel format. Cleavage and deprotection methods using wave prep. So as mentioned, the reactor fills with between 400 and 450 ml of reagents. You said that yourself. It could be a 1-to-1 ratio of ammonium hydroxide and methylamine. It could be ammonium hydroxide or methylamine on its own. Another interesting option, one that's not used too much, but the option's there, is loading with reactive gases. So you can, at the start of the run, load with ammonia gas. Already have some gas phase C&D reagent there. It's not necessarily needed. It's pretty rare that we see it used. Most places will just use liquid phase and generate the reactive gas using that. There's also the option of pressurizing with nitrogen or any other inert gas. Again, it's not needed. It may help with permeation of ammonia into the columns or wells and for C&D, but not something that's particularly needed. We're heating the reactor to somewhere between 40 and 90 degrees, depending on the oligo, with a process time of between half an hour and 60 minutes. In some cases, we will go longer. This is the sort of method that we'd input into wave prep. So obviously this varies, but in this example, we've got a 9-minute ramp using 1,200 watts of energy, so not all the energy, up to 80 degrees. We've put a pressure safety limit of 17 bar. Once we hit 80 degrees, we'll have a 12-minute hold. And at the end of that, it'll automatically commence the cooling, the pumping of our C&D reagent out of the reactor, the purging. It'll then alert you to unclamp and open up the system. This is the terminal that comes with WavePrep. So it's separate from the system. It allows you for full control. You'll be able to see the trace that we mentioned. You'll also be able to access method libraries or any methods that you've created. It'll allow you to create new methods. You've got access to application support and maintenance support. And it's also fully 21 CFR Part 11 compliant. So you'll have different access levels if you want them, and full traceability and run histories. WavePrep doesn't necessarily have to be used in a fume cupboard. It can be used just on a benchtop. We have an extendable cord for this terminal, so you can have your terminal outside of the fume cupboard and WavePrep inside the fume cupboard, just for an extra level of safety there. So what are the benefits of WavePrep? So just to finish, let's have a quick look at some summary benefits. So firstly, it's the fast and enhanced throughput. We're removing that evaporation step. We're able to perform in cleavage and deprotection simultaneously. And there's also fewer methods for all of the different types of oligos that you may come across. There's improved safety and optimization. So there's no risk, no exposure of chemicals at any point. It's dealt with from loading into the system and removing, and that's done completely automatically. We're getting better results, so superior temperature control, no cross-contamination, and excellent deprotection and cleavage yields, even with oligos with tricky protective groups and linkers. Also, it's really easy implementation. So any way in which we get our oligos into that reactor, cleavage and deprotection will work with pretty much the same method. So to finish, it's really easy to say all these things without actually showing you data. So we've got the data to back it up. So I'm going to be showing you a application report that we produced in collaboration with LGC in Denmark. So these are one of our flagship users, and they very kindly helped us generate this application report. We're going to be comparing methods that they used to use on the traditional techniques they used to use in their oligos versus using the same oligos in WavePrep. So let's look at the different methods that we're going to be using. So if we focus on the first two here, for all of these, we're using the same identical 26-mer, so same sequence of 26 nucleotides. In the first case, we're changing the linker type. So we're changing the linker that's connecting the oligo to the solid support. Traditionally, LGC were using two different methods. So ammonium hydroxide for 5 hours at 60 degrees, and for the universal linker, they're using 8 hours at 55 degrees. In WavePrep, we're going to be doing all of these methods at the same conditions. And then for the second three, we're looking at the same linker type, but different quenches and dye groups. Again, they have a number of different methods for these and different temperatures. For WavePrep, we're going to be using the exact same method. So what results did we get? For the yield, we can see that it's extremely comparable, if not higher in some cases. And that's with different linker types and with the more complex oligos with the quenches and dyes. Secondly, when we're measuring purity using UPLC or MS, again, we're getting really comparable and in some cases higher purity levels. This is incredibly impressive if you consider that we're using the exact same method for all of these. It might be the case that we could get even higher purity levels and yields by slightly tweaking the WavePrep method, but here we're just using one method. And some labs we wouldn't mind just using one method. Others would like to tweak it and have different methods slightly tweaked for each oligo to further boost these purities and yields. considering we're just using one method that's saving us even up to 6 hours compared to their traditional methods, these are really excellent results. So this full application report is available. It's a really excellent read. If anyone's interested, please feel free to get in touch, and more than happy to share this and talk you through it. But that brings this wave prep webinar to a close. I thank you very much for listening. I believe Duncan is still around if there's any questions.
Absolutely. Yes, thank you very much for that, Alex. That was great. Hope everyone's enjoyed listening to that. It's a really novel approach for the C&D work. So it was really interesting to learn about that. Thanks, Alex. Just before we do shut this down, we have had just one question. So you've obviously done a very good job explaining that, Alex.
That's what it is, yeah.
So it just says, does the system have to be in a fume cupboard?
Yeah, good question. No, it doesn't. So it's fully exhaust the system itself. Also, that pump station that we mentioned, each of those bottles is individually exhaust. Again, some users might want to still put it in the fume cupboard, and that's completely up to them. So it's really up to you. There's no actual demand. You can have it just connected to your standard exhaust line, or you can even have it attached to a fume cupboard, but it doesn't necessarily have to be in it.
Perfect. There hasn't been any more, so we're obviously approaching the 40-minute mark. So we will draw this to a close. We've got the recording that will be available. So I did put the email address in the chat, but if anyone wants to request that, they can do. And also that application note that Alex just showed there on the last few slides. If anybody does want that, then obviously reach out and get in touch. But other than that, we will say thank you very much for joining us again on this, and thank you very much for Alex for presenting. Have a great day.
Thanks, guys.
Thank you.